What up, everybody? Welcome to Exam Prep. My name is Paul. Hopefully you know who I am. If you don't, welcome to the stream. It is Wednesday night, 7 p.m. Central Standard Time, and we're going to look and talk code. We're going to look and take some of your questions, and I guess I should probably put the chat viewer up on the screen and move me to the left. Hopefully it works, and we'll be able to get going. What's up, William? Thanks for coming. I see you. I see you up there in the stream. So, again, informal. There's no protocol here. We're just looking at code, talking code, maybe dabbling in the Fast Tracks program a little bit. We're going to look at some calculations tonight. We're going to be all over the board. I don't have a whole lot of time tonight, so I can't do 3 hours like I usually do. So we will do some calculations and talk about typical things that you're probably going to see on an electrical exam. Pretty typical concepts that we're going to look at. The question that I still seem to get from students a lot. Hey, Chris, did you? Cool. Hopefully Brittany, she usually responds to my stuff as me in my emails a lot of times, unless it's technical. Then, of course, it's me because she don't know anything about electrical. But hopefully your keys will come to you and get you, I don't know if they have already. Sometimes we're quick. Sometimes it can take a day or 2 or 3. Sometimes we're pretty quick. It just depends on when it gets, how available the LMS system is to get you your information logged in. So you might have already got your email already. Sometimes we're pretty quick. Sometimes it takes a couple of days to do it. But anyway, thank you for coming. Thanks for getting the Fast Tracks program. You'll get excited. That's going to be a great program. What's up, Kevin? Glad you're here. And Moses, thank you. Hey, William, yeah, were we doing emails back and forth? Is that what we were? Was William? I'm sorry, I'm terrible with names. I get so many calls because everybody knows they can call me if they need me. I usually will answer. Hey, Todd, just got off the phone with Todd a few minutes ago. So, yeah, cool, William. Hopefully, I answered your question. Again, sometimes I answer questions for folks, and you got to remember that I do get thousands of questions, so I try to answer them all. Sometimes if I come across short, it's not intentionally. I'm just trying to consolidate the different things that I talk about. But some of the real important things that I get from people still is conductors, and the electrical exams are usually pretty heavily embedded with conductor questions or overcurrent protective device questions and the calculations. And what I tell people is whether it's a residential, commercial program, I have videos, for example, on motors. You should watch the motor video. That's going to give you the basic calculations that you need. Okay. And they're pretty straightforward calculations. Now, I'm going to try to do some mental gymnastics tonight because I am in the middle of a production series and I didn't want to use all the buttons on my console to have all these PowerPoint presentations come up. So you got to bear with me. Tonight, it's just me winging it. And hopefully I can bring each one of them up and it'll work. But again, I got about 4 of them loaded so we can just kind of jump around and then answer any questions you might have. One of the biggest questions that I see on exams is people asking about conductor sizing. And it gets real confusing for people when it comes to conductor sizing and everything that's associated with conductors. So we'll talk about the calculations when it comes to continuous load, non-continuous load, dealing with branch circuits. It applies the same thing to feeders. And that type of, because that's the big, I think, misconception that people have is that calculations, you have to have a lot of experience in, let's say, algebra. That's just not true. Whoever tells you that is trying to bolster because they have their license and they want you to think that that's some kind of pedestal that you can't achieve. It's not true. Most of the electrical questions on an exam are pretty doggone basic, and you shouldn't fear them. If you understand how to use the Ohm's law wheel, and we'll look at voltage drop again, but I do remind you, I don't want to go too deep into those topics because I've got videos on that, and those are pretty deep topics. And so hopefully, and it's still frustrating for me, I'm going to be honest with you. I was just looking how scruffy I look. I'm going to be honest with you. I see our Facebook page, and a lot of people ask, you know, do you have a video on this and video on that and video on this? And I must be doing a pretty poor job of making sure that people can find my stuff on the YouTube channel, because I've got videos on transformers. I've got videos on pools, spas, hot tubs. We have videos on motors. We have videos on derating demystified, conductor sizing. We have on ranges. We have one on dryers. Basically, everything you need to know when it comes to calculations to pass an exam, we have a video for. So most of the time, believe it or not, people don't struggle, at least in my experience. People don't, they think they struggle. But if you watch the videos and really pay attention, and you got to pay attention, some of them can get very difficult. And explaining it, like William can attest to that probably, is that you have to maybe watch it a time or two or pause it or whatever, and it can consume a lot of time. But that's the kind of stuff that you're going to get on an exam. They're not going to be overly complicated. As long as you know how to use Ohm's law, Watt's law, and do those type of things, you're going to be okay. You're not going to have that big of a problem with it. So I think people stress that out way too much. What I find that the majority of the people fail is the code lookup portion. Okay, that's the one that I think most people, because you only have a certain amount of time per question, and so it makes it a little more difficult. But I will tell you, what's going to serve you well is if you're studying, that you know how to do the optional and standard methods, and that you know how to do them, and you know how to do each little piece, because those questions are kind of low-hanging fruit that's going to be on things like exams and whatnot, right? That's what you're dealing with. Now, while I'm at it real quick, guys, I want to make sure I open up my code book, because I didn't have the code book open. I was not overly prepared tonight for what I was dealing with some wild stuff today at work. So, okay, sorry about that. Okay, so, hey, Elwood, I see you in there. All right, so first thing we're going to try to do is I'm going to try to go to the PowerPoint, and we'll kind of do some quick look at some of the stuff that you just need to know, and I'll go over it pretty quickly. So if you have any question, feel free to slow me down and say, can you explain this in a little more detail? But it's important things to remember for exams, okay? Not just exams, but life. So it's kind of some basic calcs, all right, to start off, kind of ease ourselves into it. And then we'll look at some exam questions later if we got time, but we'll kind of go into this. So let's go over. So the first one you'll see, this one is when we're dealing with load calcs, okay? And I'm trying to get your questions so you guys have it up on the board, and I'll regurgitate it because I don't have the thing up on here for you guys to see it, everybody's question. So a couple things that I'll remind you to be aware of is, as you're going through the code, and again, this is 2017 code, but it's going to be the same for the 2020. It's not going to make a difference. Is that you have to be aware of terminal limitations, and terminal limitations being 110.14c. So let's kind of remember that and understand that when you're dealing with terminal limitations, I might do adjustment and corrections on a conductor due to a number of conductors bundling, or I might have an issue where I'm worried about temperatures above the normal 86 degrees application. 30 degree, 86 degrees, or whatever I'm dealing at 310, 15, B16, I need to do some type of adjustment and correction. And I should make sure that this is working too real quick, guys. So before I get too deep in this, I want to make sure that this is working. And yeah, okay. Yeah, 30 degrees and 86, but I need to know that that's on the screen. It looks like it is. Okay, good. I want to make sure that everything is working tonight before I start jumping around from different things. Let's go back to the PowerPoint. Okay, so just remember that typically a termination is, if you're going to be under 100 amperes, it's 60 degree ampacity values. If it's over 100 amps, then it's going to be 75 degrees C. But remember, we can use the 90 degree rated insulation and the 90 degree ampacity values on your exam for adjustment and correction purposes only. Now, make it simple. If I have a load and I have no adjustment and corrections, then remember, I'm limited to the terminals. So I'm just going to pull straight from whatever the terminal rating is, and that is a 75 degree column, right? So while if I have, like in the screen, if I have a 90 degree C conductor, but I don't have any adjustments or corrections for the number of conductors or for ambient temperatures, then I'm still limited by that terminal. And if that terminal is rated 75 degrees C, for example, then I'm going to pull from the 75 degree column. If it's rated 60 degree terminals, I'm going to be 60 degree column, okay? If it's a 90 degree rated insulation and the terminal is rated 60, 75, I'm still going to pull from the 75 degree column, okay? So if I didn't know what the terminal's rating was and I didn't know anything in the equation of the conductor, you didn't know the markings on the conductor, then I'm going to have to go with what? I'm going to have to go with the limitation for under 100 amps at 60 degrees column or over 100 at 75, okay? Bear with me while Okay, so this is our terminal limitation right here, and we'll get into an example. So here's C1 that you hear me talking about. All right, just monitoring for any questions here real quick as we get into this. All right, so terminal limitation, again, the first one is 100 amperes or less, and of course I said over 100 amps or 100 amps or less. So one, if you had no markings on anything, okay, then it would be 100 amps or less in the size of conductors, which you can verify the copper size. Then it would be 14 through 1. You're just going to default to the 60 degree column for ampacity, just point blank. Well, in the real world and on exams, they're probably going to give you that it's THHN, THWN-2. So we know the installation's rated for 90. So if it was these sizes, be 14 and 1, or if it was 100 amps or less, but we know that the insulation is rated higher, then we can utilize, for example, option 2. And as conductors with a higher temperature rating, provided the ampacity of such conductors is determined based on the 60. Okay, so I could use a higher, but if it falls 100 amps or less or 14 through 1, then I would still be in the 60. Okay, however, I have option 3. And this is what most people use for this one. Conductors with a higher temperature rating if the equipment is listed and identified for use with such conductors. So this is an example where even though the conductors might be 14 through 1, and it might be 100 amps or less, if the insulation is rated higher and the terminals are rated higher, then I can ignore this 60 degrees C and say, okay, I can utilize it at 75 degree rating for the ampacity on this conductor's insulation if it's higher, okay? But everything else has to match. The lugs have to be 75, the loads lugs have to be 75, and the insulation has to be at least 75. And in the real world, that's what we get every day. That's what the THHN, THWN-2 is obviously a higher insulation rating. So we're only limited by the terminals. So be careful on an exam when it's talking about terminals. So the concept is, again, compare the conductor, compare the terminals, compare the loads. And again, like Elwood says, it's a weakest link. Whichever is the weakest link, you're bound by it. So if I had 90-degree rated insulated conductors and the terminals at the receptacle were rated 75, but the breaker for some reason is rated 60, then I'm going to be limited to 60. Okay? If they're all equation of everything is in there is all rated 75 or greater, then I use 75. I'm never going to use 90 unless the lugs are actually rated for 90. Okay? The device is rated for 90. On exams, another thing to remember if it asks this kind of question for motor sizing is motors marked with the B, C, or D, and most of the motors on your exams are going to be design B, just as inherently. Conductors that have an insulation at 75 degrees C or higher, means 75 or 90, shall be permitted to be used provided the ampacity of such conductors does not exceed 75. So you're going to treat it as 75, but you can use an insulated conductor that is 75 or even 90 degrees C. Okay? So see, this is under typically starts out being 60 degrees C, but you get a bunch of allowances in here for you to be able to use it at the 75, provided everything's rated 75 or higher. And in this case, for motors, if it's a design B, then you can just assume that it's going to be rated 75 degree terminals. And as long as the insulation is rated 75 degrees or higher, then you're okay. Williams says, if the exam question does not say it is still 6 degree. Now, so William, what you get on mostly on the exams is they're going to give you the conductor. And you need to know that the conductor by proxy is going to tell you what type of insulation it is. Okay? But if they don't give you enough information and the question is asking you something and it's giving you sizes and whatnot, that's a trigger to say, okay, probably need to use the 60 degree because you're not giving me enough information to be able to use the 75. Great point, William. So keep that in mind. They have to give you they have to give you what they want to add for the question. Okay? And they can't just assume that you know that all the terminals are rated for 75. They can't assume that you know that the load end lugs are rated for 75. Okay? So it's a very good point that William brings up. They could give you an equation, say it's 40 amps. And they could give you a conductor size. And they want to know what the ampacity is of a conductor. If they're not telling you what the lugs are or anything like that, okay, you just got to read the question and make sure that you answer all the aspects of that question. Now, conversely, if you're dealing with over 100 amperes, okay, this is where you're going to have, if you're dealing with over 100 amperes or conductors marked larger than 1, okay, so we probably should say, most time we would say 1 aught and larger, then what happens is we're going to default to 75 degrees C, and that's going to be the ampacity value, 75 degrees C, okay? Just remember, we can use 90 for adjustment and corrections, as long as the resulting ampacities of our load do not exceed that of the 75 degree column. And we're going to get into that in a second because that's another second point that you just need to be aware of. I just want to make sure that you have your foundation down. If it's, 100 amps or less, it's 60 degrees C unless something tells you otherwise that you can jump up to 75, okay? Now, that motor might be one. It might say it's a Class B motor, and then you just need to know that even if it was under 100 amperes, or those conductor sizes 14 to 1, okay, you just need to know that I can use 75. Why? Because that's what it allowed right here in item number 4. Where you're inside, you're thinking, well, wait a minute, it falls under this, it needs to be 60. But this is telling you that the terminals are okay for 75. So that's kind of low-hanging fruit on an exam, but they always seem to want to use letter B, or code letter B. Okay, seems to be what I see the most. In Texas, I can tell you that's for what they're going to use, the B. Okay, all right. Now, we didn't do anything about adjustments. We didn't talk any about corrections. We didn't deal anything that. Okay, So we were just looking at terminal limitations, okay? Now, another thing to remember on an exam, if they give you a question that has to do with loads, remember that the load is the load, okay? When somebody says continuous load, and we know to apply 125% for a continuous load, that's not the actual load. That's going to help you on an exam because the load is, if it was, let's just go with example. Let's say we had 39 amps of continuous load. Well, 39 amps is the load. It's not 39 amps times 125% is the load. The load is still just 39 amps. So careful with that, on an exam. Now, when we're sizing conductors for continuous load, then we're going to do the 125%, okay, and size the conductor. And that's going to force us to size a breaker accordingly so that when we do this inversely, now we're going to size the breaker and we do that times 80%, which is reciprocal of 125. Then you'll notice that that everything works out. Either way you work it. So on an exam, if they tell me the breaker size and want me to limit the conductors to 80%, then I just take the breaker, okay, times 80%, and then that's the ampacity of that conductor that I can't exceed as a continuous load. If they tell me the continuous load is 39 amps, then I'm going to go 39 times 1.25, and that is 48.75. And so it would be not correspond to a breaker, so I would go up to a 50 amp breaker. Okay, so now if I go to the 50 amp breaker and they say, oh, what's the largest size conductor for continuous load can be placed on the conductor? So you would go 50 times 80%, okay, and that is 40 amps of actual load. That's continuous load. And remember, ours was 39, so that's perfectly fine. Everything's good. Let's see. Oh, it says 39 is also before adjustment and corrections. Yes, so the 39 amps for continuous load, that is just the load. That's just the load itself. If we're going to do adjustment and corrections, that only applies to when we start using the ampacity values for the conductor. Remember, we're just starting out with the load. What's your load? 39 amps. Is it a continuous load or is it a non-continuous load? Well, it's a non-continuous load. Then it's just 39 amps. No, it's a continuous load. Still just 39 amps. But because of the rules in the code, we have to take it a continuous load at 125%. It doesn't change the actual load itself. That's a concept that apprentices have the hardest time gathering. The load didn't change. It's just based on a calculation. The load's still the load. That's it. So when we're doing branch circuits, 210.19 tells me that I take continuous loads at 125% and I take non-continuous loads at 100%, whatever the load is. So if I have 39 amps of continuous load and I have 39 amps of non-continuous load, what's the load? Still 39 amps for the non-continuous and 39 amps for the continuous. Now, when it comes to sizing conductors and sizing overcurrent devices, now is when we have to throw the 125% onto the continuous load. Okay? So if you can grasp that concept, you're not going to have any problem generally with conductor sizing, but we'll run through an example. So we all know, you should know, that a continuous load is anything that's on for 3 hours or more, and it's continuous if it's the maximum, okay, the maximum current. All right? So people ask me a range. A range in a home pulls a lot of current at different times. It cycles on and off. That is not a continuous load. There are very little continuous loads in a dwelling anyway, but why is that not a continuous load? Because none of those elements in the oven are not all on at their maximum output for 3 hours or more. They come on and go off. 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 There is literally nothing, and I'll preface this by saying there's literally nothing in a residential that is continuous loads unless the National Electrical Code tells you it's a continuous load. For example, for branch circuit sizing, water heaters, a continuous load. But not when we treat it for the load calculation, we don't worry about the fact that it's a continuous load. But when it comes to branch circuit sizing, it's a continuous load, okay? Because conceivably, the water heater could be on for 3 hours or more. Okay, so, but regardless of that, the code says it is a continuous load. And so anytime the code tells you something continuous load, just know that you're going to have to apply 125% to that load value. Remember, it doesn't change the load. I have to add the 125, this mythical extra 25%, so that we can protect the breaker. You with me? That's what we do. Okay? All right, so again, so that's where we're at in that. And I'm not sure, John, what happened. Everything should still be on the screen. I don't show I lost anything. So anyway, all right. We got that out of the way? Okay. So now let's understand what that does to the breaker. Now, when we do the 125%, we're building that buffer. And that buffer is to protect the breaker. That's it. That's all it's there to do. Okay? And that's all it's there. That's all it's trying to do, is to protect the breaker. So in our case, you see here, we've got the wire, it's 90 degrees C, but we have a breaker in the equation and we have our actual load in the equation. In our case, we've been using 39 amps as the actual load. So to calculate this in an exam, for example, if I have an exam question, it says it's 39, what size conductor for 39 amps of continuous load? Okay, well, then you take the 39 times 125%, and there's your conductor. And based on what your terminals are limited to, if there's no adjustment or corrections, you just go to whatever the terminal limitations are. You go to the ampacity table. If it's 75 degree rated terminals, you just go to 75 degree, and that's it. Remember, you don't use a 90 degree unless you're dealing with adjustment or corrections. If there's no adjustment or corrections, then you do your 125% for your continuous load. You go straight to the table, whatever the terminal limitations are. You go right to that column. You go down, you pick the conductor, you move, and you're gone. You're done, right? Nothing else to do that. One of the things that serves people well is to remember, we're using the ampacity value at the 90 degree only for adjustment and corrections. Unless that breaker is rated for 90 and the lug on that load is rated for 90, then I get to use the full ampacity of that 90 degree insulated conductor. But that is a rarity. And it's certainly, only time you'd ever run into that on an exam is if they tell you point blank, the lugs are all rated 90 degrees C and the insulation's rated 90 degrees C. Then you get to use the ampacity values that are under the 90 degrees C. Okay? And you get to stay at that ampacity. But typically, that's not the case. Typically, the lug's going to be rated 75. The load lug's going to be rated 75. And the only reason you're using the 90 is because that's traditional wiring type, and it allows you to do adjustment and corrections from the 90 if you need it, knowing that you never can exceed the rating of the terminals anyway, which are 75. All we're using the 90's ampacity value is to see that after we have adjustment and corrections, do I still have a conductor that's okay to handle the load that we're dealing with? That's what we're doing. That's all we're trying to do, is making sure that it can handle the load and that we don't exceed the rating of the terminals within the 75 degree column or whatever, 60 or 75, whatever you're working with. Okay? That's all we're trying to do. Okay? Let's see here. I got a question here and I'm trying to, it's not letting me move anything here. Hold on. What is going on? Hold on, guys. I told you I was winging this thing tonight, and it is not letting me do what I want to do. Hold on here. There it goes. Let's see, Paul. Would that be a 6 cents under 100? Well, no. I mean, we just kind of discussed that, William. Is that if it's under 100, and I don't know the terminals, and I don't know the insulation of the conductors, then yes, I have to follow the 60-degree column, because all I know is the size of the conductor. And that's it. All I know is the size. But if that terminal is rated 75, and that load terminal is rated 75, and that conductor is rated 90, then I don't have to stay in the 60-degree column, even if it's less than 100 amps. That's the whole purpose of 110.14C1A, is you can be able to go down. So yes, on an exam, if they didn't tell me the breaker's rating, they didn't tell me the load rating, and all they gave me was a conductor size or ampacity of a conductor, then I'm going to be stuck in the 60-degree column, okay, if they didn't tell me anything. But most of the time, they're going to tell you the conductor size, because it's going to say it's THHN, THM, so you know it's going to be 90-degree rated insulation because of the nomenclature on the conductor. And even if they did that, and they didn't tell you the lugs at each end, even though the conductor might be THHN, 9-degree insulation, but they didn't tell you the lugs, then you're absolutely right. If it is going to be 100 amps or less, or sizes 14 through 1, absolutely, you're going to pull an ampacity value from the 60-degree column. Okay? Does that make sense? Now, if they tell you the lugs, and then they tell you it's THHN, then if it's 75-degree rated lug on the breaker right here, let's kind of look at this here. If it's 75-degree rated lug here and 75-degree rated lug here, and they're using THHN, THWN-2, it doesn't matter whether it's 14 through 1. I can use the ampacity values under the 75-degree column, or I can even use the 90 for the adjustment and correction, as long as my values don't exceed that of the 75-degree column. Why? Because of these limitations. Now, if it were to say in an exam question that the breaker's rated 75, but the load lug is rated 60, and they use 9-degree rated insulation, then you know that you're still going to have to pull the value from the 60-degree column because of the weakest link. The loads terminal is only rated for 60. Okay? So there you go. Then you would do it that way. Make sense? Make sure that makes sense before I go on to that. So incidentally, the buffer is really to protect the overcurrent device. Okay, that's the buffer. But like I say, on an exam, if they don't give you all the equations, just don't forget the termination rules. Okay, 100 amps, 100 amps or less, 60-degree column. Over 100 amps, 75-degree column. However, if the insulation's rated 90 degrees, okay, and all the lugs are rated for 75, then I can leave that 60 degree and then I can apply 75 degree. Remember, the only time I can ever use that 90 degree rated insulation is for adjustment and corrections, or if all of the lugs and devices and everything is also rated 90 degrees C. Then I can use the 90 degree ampacity value up front continuously. You know what I'm saying? But I encourage you to watch my D-Rating Demystified. And I encourage you to watch the range one, and I encourage you to watch the dryer one, all those videos, because again, we talk about the different things. It says, yeah, buffering, it's going to be on your end. It's not going to be on my end, so it might be your internet connections, probably weak tonight. Okay. So I don't really control any of that part of it. All right, so let's go to the next question here. Again, we understand what a continuous load is. Continuous load. Now, in a perfect world, we wouldn't have more than 3 current carrying conductors. In a perfect world, the temperature would be 86 degrees Fahrenheit, 30 degrees Celsius. In a perfect world. We don't live in a perfect world, and neither will your exam. So your exam is going to bring in questions where it might have 6 current carrying conductors, or 10 current carrying conductors, or 8 current carrying conductors. and you might have a temperature that is 104 degrees Fahrenheit, okay, or 120 degrees Fahrenheit. So remember, you're going to have to make a correction of some type to the conductor's ampacity. The good news is that if the insulation's rated 90 degrees, which most of them are, XHHW-2, THHN, THWN-2, then we can use the ampacity value under the 90 degree column to apply those adjustment and corrections. Okay? So let's look at an example here. So in our case, we had a 6 gauge copper. All right, it's THHN as a 90 degree rated insulation. In this example, we are considering the THHN being used in a dry location. So it's copper, 90 degrees C, THHN, 6 AWG is good for 75 amps. Okay? Now we'll verify that. We'll go to the code. And we'll look at the code and we'll just verify. There it is. 6 gauge is good for 75 amps. Okay. All right. Now, we've got all that verified. The insulation's rated 90. Everything seems to be good. Okay. But that's where we're going to use. And we're going to use that 75 to apply any adjustment or corrections. Okay. Makes sense? All right. So, understanding a continuous load. So not considering any terminal at this point. We're not going to worry about this or the loads here. We're just going to kind of make sure we cover it so that you know how to do adjustment and corrections. So if there's no more than 3 current conductors and the ambient temperature is no more or less than 86 degrees Fahrenheit, then the 75 degree amps is your maximum current in amperes that a conductor can carry continuously under the conditions you use without exceeding its temperature rating or insulation ratings. Okay? So if somebody asks you on an exam question, what's the maximum current in amperes, depending on what cycle you're in, the maximum current in amperes that a conductor can carry, and they don't tell you anything about adjustments, they don't tell you anything about corrections, then you're going to pull from the 90 degree column for whatever conductor you're, because that is, and remember, 31015B16 or 31016 in the 2020 code, the ampacity values on that table is continuously, forever. It could run forever at that ampacity and never damage the insulation. But that's a perfect world. That is not more than 3 current carrying conductors. And that's an ambient temperature that is 86 degrees Fahrenheit or 30 degrees Celsius. We're not living in a perfect world. Remember, exams are never a perfect world anyway. They're going to tell you and have to give you the values. But I just want you to be aware, if I were asked what is the maximum current available on a 6 gauge conductor of THHN, then it would be 75 amps, the 90 degree column, because that's what the insulation is rated for. Now, why do we drop it down to 75? Why do we drop it down to the 60 degree ampacity columns? Because of terminal limitations. But if I had no terminal limitations at this point, that 6 gauge is good for 75 amps forever, indefinitely. Now, the moment that you start adding more than 3 current carrying conductors or change the temperature that these conductors are placed into, then it starts changing a little bit. And you have to start doing some math. Okay? So, now conditions of use are not perfect. If they were, we wouldn't have to do anything. We just go to the tables and pick it and be done. We wouldn't even have to use a 9 degree column. We just basically look at our terminals and say, well, there's 75 degree terminals. Just go to the 75 degree column. This is the ampacity of conductor, and that's it. But once you have more than 3 current carrying conductors or the temperature changes, then we have to start doing some calculations here. So let's look at it kind of an example. When we have a continuous load, maximum again, current 3 hours or more, and it has to be what? It has to be the maximum current drawn for 3 hours or more, okay? Continuously, all right? Now, that's the maximum current, okay? So if I have something that pulls, 30 amps, right? But it's only pulling 28 amps, or 27 amps or 25 amps, but it could pull 30, but it's not. It maybe has the way it operates. It's not going to pull the maximum amount. Okay, for example, a light bulb, when you turn it on, that is the maximum amount. So traditionally, that's when we have talked about commercial buildings, the lighting in a commercial building, although changes in the 2020 code, it already gets factored into the VA per square foot. But under the 2017 code, which most of you are testing on, then you need to know that the lighting loads, for example, inside of a building, commercial building, are going to be on for 3 hours or more. And when those luminaires are on, they're on. They're on. So even if they had a dimmer, it wouldn't matter because they have the potential to be at their maximum output. And so in this case, I'm going to treat them as a continuous load. And that's what I would be treating it as, a continuous load. Okay? So always kind of keep that in mind. Now, you'll notice on the screen it says the multiplier of 125%, but it also has a reciprocal of 80%. Okay? And so if I know the breaker on an exam, if you know the breaker, then you can tell you what the actual load is of continuous load that the maximum can be placed on a conductor based on this breaker by just taking the breaker's rating and doing it times 80%. And that is the maximum continuous load. Okay? Conversely, if they give you the value in continuous load, you do it at 125%, and that should equate to the breaker size. Okay? So they work conversely. So depending on what you get on a question, when you're doing that math, if they give you a breaker question and want to know what the maximum current that can be on a conductor for a continuous load, then you just simply take the breaker and do it times 80%. If they give you a conductor size, say they tell you it's a 6 gauge, and they want to know the breaker, then you do the 6 times 100, whatever the ampacity is for the 6 times 125%, and then select your breaker. Okay, so you can work it either way. So just remember that on an exam. One of the allowances in the code is called 100% rating, and very rarely do we see a breaker that's rated for 100% rating continuously. But if you get an exam question, it says the breaker is rated for 100 amps continuously, then you can take that breaker, can handle, you don't have to put, the conductor can take at 100% its rating. You don't have to do the 125% on it at all. So if it's a 100 amp breaker and it's rated for continuous loads, I can put 100 amps on it continuously and it would be okay. If that breaker's not rated for continuous load, then I could not put 100 amps on it continuously. Okay? I would have to limit that. And so I would take 100 times 80%, and obviously that's 80 amps. So I would not be able to exceed 80 amps of continuous load. Okay? So that's kind of how you would prepare for that, sizing conductors and, for whatnot for that. Let's see if we can get to example. Okay, so here's an example. So if they give it on an example, let's say they give you a question that says 50 amperes of continuous load, right? So it's 50 amperes times 125%, which is 62.5, and that's what you're going to use to go size the breaker. So you're going to go to 240.6A. Remember, the load is actually 50 amps. The calculated load of continuous load that we use to size breaker is 62.5, all because of that 125%. Just don't forget that this is the actual load right here. This is it right here. All right. So in this case, 62.5 amps. I'm going to go to 240.6A. I'm going to look at the breaker sizes, look at the handles. And again, one of the other things to remember is that for continuous loads, the breaker in 210 is going to require, and actually this should be 210.20, not 210.10. And that means that it's going to require it to be rated at 125% for continuous and 100% for non-continuous. Okay? So the breaker itself cannot be less than 125%. Okay? So there's different things that I have to work on with that. Now, notice in this case, it's a continuous load. So we did it at 125%. Okay, so we go there to 240.6a, and you'll notice there is no breaker there for 62.5 amps. Okay? And assuming the rules in 240.4b are met, which is the next size up rule, the installer would then select a 70 ampere rated circuit breaker. And that's it. So it would be a 70 amp breaker. Now, remember, if the load is non-continuous, the 125% doesn't apply to the circuit breaker, and it can handle 100% of the load. So that's another question that people ask on an exam. If I have a 100 amp breaker, or in this case, let's say a 70 amp breaker, can I put 70 amps on that breaker? Yes, as long as it's not more than 3 hours or more. I could load that thing up to 70 amps at any given time. I kind of think of it this way. You're not going to shortchange me. If I'm paying for that breaker and it's good for 70 amps, I want to get 70 amps out of it. So I will get 70 amps out of it. The only issue that we run into is if it becomes a continuous load. And then we have to do it, and that's how we're protecting the breaker. Okay? So 3 hours or more, or if it states at a continuous load. Okay? All right, so let's do this example. And again, this is an example where you have two different loads. And this is very common on an exam, so let's kind of look at this. It's a 50 amp continuous load and a 65 amp non-continuous load. So you take the first one, which is continuous load, 50 amps at 125%. That's the 62.5. We got that a minute ago. And then you take the non-continuous load at 100%, which in our case is, say, it's just 65 amps. Okay, so 65 times 100% is still just 65 amps. So the two together is 62.5 plus 65 amps is 127.5 or 128 amps. Okay, so then the installer would do like normal. You would go to the circuit breaker, 240.6a, find a breaker that can handle 128 amps. Now, this is a continuous load. Again, it's going to say that the breaker itself, even though we're looking for one, the breaker itself can't be less than 125% of the continuous load. Okay? So that's the breaker. Can't be less than that. So it might mean that when we choose the breaker, that the conductors aren't sized enough, because you got to size the conductors have to be protected by the actual breaker. Okay? So in this case, we have to size it in order to be able to do it. So in this case, we took the 128 amps. All right? Next side, we went there and we didn't see one that's 128 amps. So the installer would go to the next size to be 150 amp circuit breaker. Okay? Now remember, that we're just sizing the breaker right now. That's what we're doing here. We're sizing breakers. Okay? That's all we're doing first here. And it tells us how to do that. Again, for breaker sizing, it's 125% of the continuous load and 100% of the non-continuous load. And if you want to see that, where that says that, because this reference is, previous reference was not accurate. So I'm going to go back to the NEC. And we're back here in the NEC. And I'm going to show you that in the branch circuits. As I wait for my slow PDF to catch up. All right, so we'll go down here to... So here's 210.20. I told you it wasn't 210.10. It's actually 210.20. And here's where it says continuous and non-continuous. It says, where the branch circuit supplies continuous loads or any combination of continuous and non-continuous, the rating of the overcurrent device shall not be less than the non-continuous load plus 125% of the continuous load. Okay? So that's where we get that from. Now, that's the same for feeders as well. So, make it easy on yourself for an exam. What's good for the branch is also the same for the feeder in 215. Didn't change in 215.3. Same concept, okay? Well, not 210. Let's see here. Let me go and show you that in the feeders. Because .2 is the ratings. And let's see here. Yes, I was right. So .3 is the overcurrent protection, okay? So it tells you almost the same thing right here. Not less than non-continuous load, which is 100%, and 125% of the continuous load. So essentially says the same thing, okay? So keep it simple. Don't make it, don't try to make that overly complicated in how that applies, okay? All right. Now, let's see if I can get which one. Okay, so the next size that would be 150. Now, let's look at it, understanding the load of what we just did. Now, we have this exception that says we can use 100% of the breaker if, by chance, we have a breaker that's rated for 100% rating. How does that affect everything? Well, if you look at this equation right here, if it was a breaker that's rated for 100%, and be careful of that on an exam, if it's rated 100% for continuous loads at 100%, okay, which is in this exception, it's rated for 100% of its rating, so it's, whatever this breaker would be, so then I would not need this 25%. So basically, it would just be 50 amps plus 65 amps at 100%, okay? And basically, the 65 amps for the combined load, if you add the two together, is 115 amps. So if I go to 240.6a, doesn't have a breaker rated at 115 amps, assuming all the rules apply, the circuit breaker can be rated for 125 instead of the 150. So that's a difference. If the breaker is rated for 100% of its rating, most of them are not. Most of them are not, and if it is on an exam, they would have to tell you that, okay? So don't worry about assuming. They have got to tell you this on an exam, okay? All right, that's a lot of information to soak in. So now we can start looking at the conductor rules and kind of, because now you know how to size the breaker, right? We're clear if you get that exam question on the breaker. On the conductors, you have two examples here. You have an A and a B. So this is 210.19A1A or B. Notice there's an or in here. So firstly, when we're sizing these conductors, it says where the branch circuit supplies continuous loads or any combination of continuous and non-continuous. So remember, A has very much got to be a continuous load to come into play, okay? So if I do have continuous loads, then basically it is 125% for that conductor for the continuous load. If I also have non-continuous loads as well, then I take them at 100%. Now, what happens if I don't have continuous loads? Then I just size the conductor based on 100%. Nothing changes, okay? But if I choose my conductor sizing, then I have to compare it, okay, to B. Now, what's B? Now, B says, well, do you have any adjustment and corrections going on? And if you don't have any adjustment and corrections, remember what I said? You just take the load, you go right to whatever the terminal limitations are on the code, in the ampacity table, and you select your conductor. But if you do have adjustment and corrections, now you have to apply the adjustment and corrections. And you have to have a conductor that still has enough ampacity value to handle the actual load. And that's why you see me put actual load down here. You have to have enough for the actual load. Okay? So let's kind of look at this real quick so that you can get it. And then we'll move on to another calc for another thing. I just want to make sure you're all clear on conductors. So where a branch circuit supplies continuous or a combination of continuous and non-continuous, the minimum branch circuit conductor size shall have an allowable ampacity that is not less than the continuous load plus 125% of the continuous load. Okay, so do the calculation the same as we did in step 2. Then select the conductor size needed to handle the load. Keep in mind that if the terminals are rated, as we discussed in step 1, for 75 degrees, you will choose the ampacity from the 75-degree column in 31015B16, not the 90-degree C column. Okay? So just remember that concept when you're doing this step here. All right? You don't get to use the 90 until you're doing adjustment and corrections. I think that's where people screw up. Remember, if you're doing this option right here, number 1, right here, there's no adjustment and corrections being done. You're just taking it as a continuous load or a non-continuous load, and you're sizing a conductor accordingly. You don't get to use the 90. Okay? You're limited to your terminals. Remember what I said? Just go choose it. However, if you're going to compare it to B, because you're choosing whichever results in the larger conductor, that's what you're doing. The larger conductor wins. In this case, since I am going to be doing adjustment and corrections, I could use the 90. But we're doing the first one here, so we're only doing the A, which is the continuous load type of calculation. Okay? All right? So that's all you would do. You take whatever the load is. If it's a continuous load, basically, let me give you an example. 39 amps, continuous load. 39 times 1.25 is 48.75. I would go to the 75-degree column, okay, and choose a conductor. Again, if my insulation, in this case right here, it's 90-degree rated C. So remember, we're allowed to do that. But as William will tell you, if I didn't know the conductor size, and they will tell you on an exam, by the way, if I did not know the conductor size, then I would be in the 60-degree column. Okay? So be careful on an exam. They might be just asking you, so they have to tell you everything, okay, that's involved in here. So I do these slides so that instructors can write in whatever they want to write in, okay, in order to work the calculations. Just remember, when you're sizing it, first size for continuous and non-continuous, or even just continuous, you don't get to use the 90. You only get to use the 90 under option A1B, okay? And under A1B, then you get to do it and use the 90 for the adjustment and correction application, okay? So ignore this. This is a typo right here. So let's just look at an example. No exceptions apply. I have 45 amps of continuous load, okay? We're going to do the first one here. 45 amps of continuous load, and we're going to do it at 125%. So 45 amps times 125%. Again, don't lock yourself into the screen, guys. I tried to pull these up at the last minute, and this probably is an old one. Just listen to what I say. So again, that's going to be 56 amps. However, the maximum load to be served under the code rule is still 45 amps. The fact that being taken as a continuous load does not change the fact that the load is still 45 amps. Remember, 45 amps is still 45 amps. Okay? Don't remove the fact that it's still 45 amps of load. Now, when we're sizing the conductor for continuous load, we take that 45 at 125%, and we're going and finding a conductor that's rated for 56 amps. But just remember, 45 amps is the actual load, okay? Let's see if I can give another equation, so some feeders. All right, here's just some steps that I go through that I want to just kind of work through these tables. So these are the tables you better get yourself familiar with. 31015B2, and you'll also need to be familiar with 31015B3A, okay, and how you apply these. So we're going to look at examples, and then we're going to move on to another one. So let's look at some example here. 35 amps. So solution number 1. Remember we just went through, and then I'm going to have to move on to another question. So it's 122 degrees Fahrenheit. The terminals are rated 75 degrees C, 90 degree THHN. It's a dry location, and we're telling you it's a continuous load. So I have adjustments and corrections in here. All right. And it doesn't say how many conductors I have, so not going to come into play, it looks like. So, but I do have a temperature value. And let me make sure I get my thing up here on the screen, because I haven't seen anybody post anything since O posted. So I don't even know if I'm still streaming or not. Okay? Because nobody's saying anything or asking any questions. All right? So I'm going to test it. Okay, looks like it's working to me. All right, so let's kind of work this out. This would be very typical on an exam. Okay. Hold on here. Okay. All right, sorry, I got a little tab up in the way. All right, so this is very common on an exam, so let's work these out. All that, I just kind of built the foundation for you to work these questions. And we'll see if they're right or wrong, because this is an old one, and I just pulled the first one that I came up. All these are being redone for 2020, by the way. All right, so 35 amps of continuous load. This is kind of what, this is what the question would be like. 22 degrees Fahrenheit is the ambient. The terminals are rated 75, and it's THHN, copper. So we got everything we need. So we have to compare A1A to A1B, okay? A1A to A1B, and whichever results in the larger conductor is the one that we have to choose. It's the larger conductor that wins here. All right, so what's the actual load? 35 amps. But since it's continuous load, we take it, and this is the first one you have to compare. Remember it said take it at 125%? So I take 35 amps and work it with me if you got a calculator, because don't assume what I got on the screen is right. Again, I told you I was really behind the gun tonight. And so I just kind of rushed it. So 35 times 125% is 43.75, which is 0.75. We're going to round to 44 amperes. Okay. Now remember what I said? Because it's THHN, because the terminals are rated 75, because I don't have any adjustment or corrections, this is so important to remember. You now just go to the 75-degree column and pick your conductor. In this case, 75 would be an 8-gauge copper, which is rated for 50 amperes, can easily handle 44, okay? Not yet, Rodriguez. We're not there yet. We have to compare the continuous load option in 210.19A1A, and then we compare it to 210.19A1B, and that's where your multipliers are going to come in. See, that's where most people forget, all right? Because why we forget is because most of the time, we're going to have a condition of use, which means we're ultimately going to always be down here in A1B. Very rarely will this A1A be the option. But on an exam, you got to know, because you don't know what they're going to throw at you, okay? So in this case, since I don't have any adjustment or corrections, nothing gives me permission to use the 90-degree insulation here. I've got the terminal limitation. So that's where I would get an 8-gauge. Okay, so you would write that down. So 8-gauge is the size for that one. Now, same equation, but now we've got the 35 amps, which is the actual load, okay? And remember, B option didn't say anything about taking a load at 125%. It just says that you got to have enough ampacity to handle the actual load, okay? So this is where people get really confused at it, all right? So let's look at it this way, and then we'll kind of run the equation. So 35 amperes. Now notice I'm using division. So anytime that the question in an exam, and I'm giving you little tidbits, since the question gave me the amps, but did not give me the conductor size, then I'm going to use division to try to work my way up to select a conductor. If I already knew the conductor size, or they told me a conductor size, that I can readily go get the ampacity values from the 90-degree column, then I would use multiplication to come down. But if they give you the ampacities and tell you it's a continuous load, then you're using division to go up. So, and then you can check your work with multiplication. You'll see how this goes. All right, so 35 amps divided by 0.82. Where did the 0.82 come from? That came from this table where we have the 122 degrees Fahrenheit. So that's going to come from this table right here, 310, 15, B2A. And in our case, it was 122. Okay, so this looks like 0.82. And that's where we got the 0.82 at. So that's where we got that value at. Okay, so we're going to do this and double check our math. We're going to do 35 divided by 0.82. And that equals 42.68, which is rounds to 43 amperes. Okay, now I go to the 90 because the code says I can use the 90 for adjustment and correction. I'm going to go to the 90 and I'm going to go up. And remember, the first one, I did not have to do any adjustment and correction for A. Okay, but B, I am. So in this case, I'm going to go to a 90-degree column. And what we're going to do is we're going to select a conductor that can handle 43 amps for that. Now, if you go look at the table, and I'll do that so we can all see it. If I do that, and I go to the table, hopefully you all are doing that anyway on your code books there. And we're into the 90. Well, we can't use 10 because that's 40. We need 43. So we're at 8. Okay? So that's how we got the 8. All right? So 8 is good for 55 amps. Okay? All right? So then once it's good for 55 amps, and it's the most accurate choice. Now let's verify that it can handle the load after the application of adjustment and corrections, the actual load. Okay? So, and what was that, by the way? 35 amps, right? That was the actual load. Okay? And this is exactly what the code tells you to do in 210.19A1B. Okay? It only tells you to take it at 125% for the A1A. It does not tell you to do that for the A1B. Okay? And many people miss that. All right? So here we going down in, so we got the verified. So we take the 55 and we multiply. Remember, now we're going to multiply down. So we take the 55 and multiply it by 0.82. And that equals 45.1, which we round to 45. Now you got to ask yourself this question. Can a conductor that is good for 45 amps after adjustment and correction, can it handle 35 amps of actual load? Remember, when we took it at 125%, that was for protection of the breaker. Remember, the conductor can handle the load. That's not the issue. But now when we do this math, we need to make sure that after we apply some adjustment and corrections, which is going to lower the ampacity, that the conductor's still good to do what we need it to do, right? That's what we're doing. We're just verifying it. That's all. And in this case, a 45 amp rated conductor, because that's the new rating of this conductor now. Can it handle 35 amps of actual load? Absolutely. Absolutely. And it doesn't exceed the load that we have, the 35 amps, does not exceed the rating of the 75-degree column, which is 50 amps. So we're good here. We're totally fine to do that under the 75-degree column. Perfectly okay. An 8 gauge is perfectly fine to be sized for this. Now, that's an 8 gauge, right? Now, this one worked out easy because now when I compare A1A to A1B, both of them were resulted in an 8 gauge conductor. Now, if one of them had resulted in a 6 gauge and the other one was in an 8 gauge, then we would have had to choose the 6 gauge because this whole rule is to choose the conductor that's larger, that results in a larger conductor. Okay? So you always have to compare A1A to A1B. Now, I think what happens in the real world, we don't really do that scenario. We just we know that we have adjustment and corrections, and we just do it. Okay? Now, another thing to remember, in a lot of times in your exam questions, they won't say, they'll just ask you the ampacity of a conductor. They won't tell you anything about adjustment and corrections. If that's the case, then do it at 125% of whatever the load they give you. If they say it's a continuous load, just take it at 125%, size your breaker, size your conductor. Okay? That's simple. All right? If it's not a continuous load, size your breaker based on whatever the load is that you need. 40 amp load, size a breaker 40 amps. Okay? It's not continuous load. The 0.25 is because we had an ambient temperature of 122 degrees F. Okay? So again, that question, and I can't see my daggone notes. Hold on. Let me move this. Kevin, okay. Let me move my screen here over to the right, Kev. All right, so let's go to the code and I'll show you what I'm talking about. So it's 122 degrees. And in the code, notice that every ampacity on this table has to do with 30 degrees C and 86 degrees Fahrenheit. If it's any temperature other than that, then you're forced to have to use these tables. And since the insulation is rated 90, I can use this column because it was THHN. And whatever the temperature is in our example. So in our example, let me delete this real quick because this is misleading. I can leave that one. So in our example, it was 122, right? 122 degrees Fahrenheit. Well, that results in a 0.82, and that's your multiplier. Okay? So if you know the load, you can use division in order to pick the conductor in the 90-degree column. So that's an important thing to remember. Now, if I have two different things, let's say that same... hold on, I'm going to get ahead of myself because I am going to show you an example of that real quick. All right, so anyway, just make sure we're clear on that before I go forward. Kevin, are you clear on that? Yes. Okay, you look clear. Okay. All right. Just want to make sure you were clear. All right. All right, now, the next one is going to put the two together. So when you're dealing with more than 3 current conductors, remember that table only deals with what? Okay, is no more than 3 current conductors. Now, when I have more than 3, which is 4 or more, then I'm going to have to apply an adjustment factor. Okay, so this only applies to the number of current conductors that exceed 3, which is commonly could have been easier for them to say 4 or more, but we want to make it difficult, so we'll say more than 3 current conductors. Okay, so if it's 4 or more current carrying conductors inside of the raceway, for example, or cable assemblies, multi-conductor cables that are bundled, and you're dealing with more than 3 current carrying conductors, then I'm going to have to apply another demand factor. And that one's 31015B3A. Okay? So again, we're going to look at an example for that. And that's this table here we just looked at. Okay? And it's going to be, now I don't know why they didn't do these just like the other table and put like .80, .70, .50, .45, it seems like that would be, makes sense to harmonize all that. But you know that to do that, you move 2 decimal places to the left, and it's points. So you start from the right and you move to the left. So you're converting this percentage value into a decimal value in order to be able to use it for a calculation. And I show you that right here. See, 80%, you move it to the left 2 places, and it'd be 0.80 for your calculation. All right. So what does that mean? That see that when you have a number of current carrying conductors in a raceway, they all give off heat. So when you start to get 4 or more, then it's called mutual heating. And the ampacity of a conductor starts to really drop. So you have to be careful when you start getting 4 or more. Okay? All right, so, and this example right here, let's look at the examples. Number 1, step. The load is 35 amps. Number of conductors are 6 of them, let's say, in a raceway. So it exceeds 3, okay? Exceeds the maximum of 3, so there's 6 of them in there. Remember that the terminals are limited to 75 degrees C column, as discussed. We can correct from since it was THHN, remember, here's the example right here. THHN, 6 conductors, 35 amps of non-continuous load. Okay, we'll do this one as a non-continuous load. then what we're going to do, if you get one of these questions on the exam, you can use the 90 for adjustment and correction, and we do exactly the same thing that we did for the ambient. Okay? Same thing. You take the 35 amps of actual load, and you divide it by 0.80, which gives you 43.75 or 44, and then you go and you pick a conductor. And we did the same thing we did before. And it's not going to change because the other one you remember was 0.82. This one's 0.80. It's going to be a very similar calculation. All right? So 35 divided by 0.80 gives you 43.75 or 44 amps. You go to the 9-degree column. Why? Because you're doing an adjustment and correction. Okay? It's something different than what the tables is 30 degrees C or 86 Fahrenheit, and you're dealing with more than 3 current carrying conductors. So I get to use 90 if the insulation is rated for 90. And of course, ours was, it's THHN. So once I select 55, now I can check my work. Then you use multiplication to work your way backwards. So 55 times 0.80 is 44 amperes. Okay? Can a conductor, this new ampacity now, this conductor, after you apply this mutual heating effect that takes place, I've got a new conductor that has a new ampacity value of 44 amps. Can that 44 amp conductor handle 35 amps of actual load? Absolutely. And that actual load of the actual load of 35 amps does not exceed the 50 amps under the 75-degree column, so we're perfectly okay. Okay? So now, let's look at it for a continuous load, 35 amps. Same concept. 35 amps continuous load, okay? Notice what we don't do here is we don't really change anything when it comes to this. First thing we do is same thing, 35 amps of actual load divided by 80% or 0.80, 43.75 or 44 amps. Now, as we did with the ambient, we have to apply the rules of 210.19A1A and A1B and select the largest of the conductors. Okay? So how do we do that? Well, we got to work it out. So 35 amps of continuous load, 6 conductors, dry locations, 75-degree terminals. We already did that. That's 44 amperes. So looking at 31015B16, 9-degree column, we did an 8 gauge, good for 55 amps. Okay? And we verified that by 55 amps times 0.80 is 44. Can that handle the load? Absolutely. We're good there. Now, we have to compare. Remember what we said? We're going to compare. So we've looked at it either way, so now let's do it. So remember we said it was 35 amps? Well, A1A says I have to take that at 125% and size my conductor. So it was, again, pretty easy. 35 times 125% is 44 amps. We rounded to 44. I go to the 75-degree column. Remember, I'm not using the 90. I'm using 75 because I didn't do any adjustment or correction here. I'm just applying continuous load rules. And that's an 8 gauge. Okay? Good, 50 amps. Now, compare it down here, 35 amps. And now I'm comparing it, and I get to use the 90 value for adjustment and corrections. So, again, it was 44 amps. Okay? And so it's, remember, we're using division, so we're going up. And 44 amps. Now go to the 9-degree column, 31015B16. Select one that's good for 44 amps. It's an 8 gauge, which obviously is good for 55 amps. And, okay. So how do we do this? Well, the 8 gauge is good for 55 amps. We do that times 0.80 to see if we're okay to be able to handle the load. And we can, because it equals 44 amps, which can handle 35 amps of actual load with no problem. So in this case, A1A, it also resulted in an 8 gauge. A1B resulted in an 8 gauge. All we have to do is since they're both 8 gauge, then it's 8 gauge. If one had been larger, we have to go with the larger one. Okay? Makes sense? All right, and this is where we got all the values at, okay, and I won't go into the neutral conductors. It's not going to make any difference for this type of thing. All right, let's go real quick over to, let's see if I can do this without screwing it up. Oh, that's me. And it looks like that I'm on the optional, I don't want that, standard method. Okay, now before I get into the standard method, do I have any additional question? All right, I keep getting the same question, and this is why I go over this. I have to clarify this for people. Look, I told you what the lugs were. I get frustrated because this is probably the number one, and either I do a poor job of explaining it, or it's just really a complicated topic, and it's the reason I have to teach it over and over again. The question that we use, the premise, okay, told you that the terminals are rated 75. The conductor's rated for 90. Okay, so when we're working these questions, I've already told you that the terminals are 75, so you would not use the 60 degree. Okay, because I told you that the terminals are all rated for 75. But if by chance, I know, Larry, I'm just giving you a hard time. If by chance they did not tell you the terminals, absolutely remember that you'd have to use the 60 degree. They have to tell you, okay? Otherwise, they're giving you a crappy question because, again, everything is based on the weakest link, whether it's the terminals or the conductor's insulation or the lugs at the end load or whatever it is on a device or whatnot. We have to know. So most of the time on exams, believe it or not, and I know this is, I joke, it is frustrating a lot of times, they have to give you these values. It would not be fair on an exam. And if they don't give you an exam question, I don't know if you get it wrong or not, but if you did know, I would contest the question because they need to tell you the terminal. Now, if they don't tell you the terminal rating, then they're basically, depending on the size of the conductor or the ampacity, they're trying to force you to realize that you can't use what? I mean, if the lug was rated 60 degrees C, okay, and the conductor is rated for 90 degrees C, I can use a 90 degrees C for adjustment and corrections. I just can't exceed the value under the 60 degree column. Okay, so kind of, it's no different than what we did for 75. You would do the same thing for the 60. But I can always use the higher rated insulation for adjustment and correction purposes, as long as I remember that I'm beholden to whatever the terminal limitations are in 110.14c. Okay? So if I did this same calculation, Larry, and I didn't tell you the lug rating is 75 degrees C, let's say I didn't tell you what that was, all right? So then the application would be, so it's still 35 amps of load, okay? The load didn't change, it'd still be 35 amps. And I would divide that by 0.80. So I'm going to do it, 0.80 at 43.75 or 44 amps. I'm still going to go to the 90 because the insulation might be rated for 90. And I'm going to pick, let's in this case, say 55 amperes. Okay? All right. Well, in this case right here, once I had the 55 amperes from the 90, I do the same thing I did, and I tell you my conductor's new rating is still going to be 44 amps. However, I then need to go to column C because of the 60, and my actual load itself can't exceed 40. And my actual load here is 35 amps. So my 35 amps would not exceed the 40, so it still would be okay for an 8 gauge. Make sense? So just a matter of what you're checking. You just want to make sure that the actual load can still be handled based on whatever the column you're working out of. All we're using the 90 for is for adjustment and corrections. That's it. At the end of the day, we still got to make sure. Here's the easiest way that I explain this. And I'm trying to explain this the easiest way. The only reason we're using the 90 is to find out what my conductor's ampacity is after we apply all those conditions of use. And now once I have a new conductor's ampacity, then depending on whether I'm in it doesn't matter whether I'm in the 75 or the 60 at this point. This is the conductor's ampacity. This is it. But now I got to go back and look at my load. And my load cannot exceed the value that's in the 60 degree or the 75 degree, depending on what my terminals are. So in this case, it's only 35 amps. So my conductor is still good for 44 amps. Now I shift gears and I go back to the terminals. And since, let's say it didn't say 75, it was blank, then and because of the sizes we're dealing with, you're absolutely right. I'm going to go to the 60 degree column. Now I'm going to look at that 60 degree column. I'm going to say, wait a minute, my conductor is good for 44 amps, but under the 60 degree column, the maximum is 40 amps. What is my load now? And my load is 35 amps. It's still okay for it to be an 8 gauge under the 60 degree column. Okay? All right? So, and the other thing that I explained to people, you only use the continuous load, okay, in a question that says this conductor is rated continuous load, you take it at 125%. If there's adjustment and corrections, then you utilize the option that uses the 90 degrees C insulation, okay, on an exam. All right? That's the equation. Now, when people say, well, wait a minute, I don't do that, Paul, when I'm sizing it to a water heater. I just take it at 125%. Yeah, because it's a continuous load and there's obviously not going to be more than 3 current carrying conductors in it, right? But you could have an ambient adjustment. And if you have an ambient adjustment, then I have to compare it to 210.19A1B. And whichever one results in the larger conductor, then I accept. I take that, okay? So we can work that out if you want to do that. Let's do one. So it's a water heater, and we're just running a 10.2 to it, okay? So we're just running a 10.2 to the water heater, 240 volts. We're just going to do that, okay? We'll run 10.2. So it's not more than 3 current conductors? Check. It's probably in the building, so it's probably not going to, most people, it's a conditioned space. It's not going to be higher than the 30 degrees C, 86 degree Fahrenheit. Okay? But let's lie for a second and say it is. Let's say it's 104 degrees Fahrenheit. If you ever wondered why we don't do this generally for those runs, now if it runs through an attic, people don't do this, but they probably should because the ambient temperature up there is a lot higher. So let's assume our water heater running through the attic and it's 104. How would we work that? Okay. So we know it's going to be a 10.2 with ground. Okay. And we'll assume we'll say that we take that at whatever the elements are for the continuous load. And in your mind, you're thinking, okay, what do I apply as a continuous load? Whatever the value is on the nameplate of the water heater, you take it at 125% and you size it, right? Makes sense? Okay. Now, if I take the conductor and compare, then that would be whatever the load is at 125%, and that's my conductor size. And let's say it's a 10 gauge. Now, in the code, you compare that by going to the code and say, okay, the 10 gauge, okay, 10 gauge, good for 40 amperes, okay, under the 90, good for 40. So now I get to apply those adjustment and corrections, and it was 104, so I can go 40 times, since I already know the size, it's a 10, that was what was selected for the other, I'll go 10, and then I could go up here to 104, which is 0.91, okay, and I can do 40 times 0.91, and it's 36.4, okay, so it can handle 36.4 amps, and it's still a 10. So as you can see, the reason we don't get into this in big detail is because it's not going to make a difference either way. Both of them would have resulted in a 10 gauge. So most people don't think about these things. They just calculate them out. But in the real world, it's different than on the exam. An exam, they might give it to you in two different ways. They might give you the ampacity, they might give you the conductor size, and you have to be able to go look up the ampacities, or if they tell you the continuous load, they'll tell you the load and treat it continuously, and you do it that way. Okay? Water heaters, for example, have the nameplates, and you follow the values that are on the nameplate. Okay? And you take that at 125%. Real quick, because I think I was still on there. Let's go to the PowerPoint. All right, so let me turn that one off, and we go to the standard method PowerPoint. And I'll just kind of give you some hints. Remember, the first thing you're going to do in a residential calculation on an exam, they're going to give you dimensions. You want to take those dimensions, and you're going to do the length times the width. Okay, so in this case, it's 35 by 55 feet. And so that would be 1,925 square feet. Now, in this example, they told me there was a porch. And remember, the porch is the 7 by 10. Those aren't included in your calculation, so you subtract that away. So if they give you that in an exam, just be aware of that, because open porches, garages, and unused portions or unfinished spaces that are not adaptable for future use, they don't get counted. So you make sure you take those out of your equation. Just remember, 3 VA per square foot is what you're going to use on dwellings, okay, for the application. So in this case here, it was 1,925 minus 70 square feet, which is 7 times 10. That is 1,855 square feet times 3 VA. You're going to get that value in 220.12. And if you're in the 2020 code, it says we're gone. I don't know. My stream says I'm not gone, so I don't know. Check your connection. All right. So again, the 1,855 square feet times 3 VA. So it's 5,565 VA. Okay. So just remember that on an exam. Now in the Fast Tracks program, we actually walk you through each one of these little steps. Okay. But I'm just kind of giving you some values that you might see in calculations. And again, if anybody's having trouble seeing the screen or the monitor, you lose connection, it's going to be on your end. It's not going to be on my end. Okay, it's going to be on your connection, your download speed. All right, so let's kind of look at some things. Remember, you're going to use for your calculations when they ask you about small appliance branch circuits, you're going to have a minimum of 2. But on an exam for calculation, they could give you more. So in my example, I call for 6 small appliance branch circuits. 4 of them. I don't know where I got 6 from. 4 of them. So it's 1,500 VA each. Okay? But just remember, if they ask you on an exam, you need a minimum of 2. You got to have at least 2 small appliance branch circuits, and they're 1,500 VA each. Okay? Each. All right? Now, where is the requirement in the code for these small appliance branch circuits? 210.11c1 is the requirement, and the code reference that tells you to take them at 1,500 VA is under 220.52b. That's what tells you that they each count for 1,500 VA, and you got to have at least 2. Okay. In our equation, we had 4 of them, so you're going to take for all of them, so that's 6,000 VA. Laundry. In our example, we had 2. Watch your question on your exam real closely, okay? Because, again, you're only required to have at least 1. In a normal single-family dwelling, for example, you'd have at least 1. But be careful, because your question on your exam could say more than 1. And if it does say more than 1, then you have to account for more than 1. So in our case, we had 2 laundry circuits, so that would be 1,500 VA each, okay? And, again, the requirement to have at least 1 laundry circuit, there is an exception to that rule, but for generally, you're going to have the laundry circuit, and that's 210.11c2. And again, you're going to get the values in VA under 220.52. And that's what's going to give you the values that it counts as 1500 VA. Okay? Just remember those things. Now, if you get an exam question, a calculation question that says, tell me what the general lighting and receptacle load is for the small appliance branch circuit in the laundry. Or it just asks you and says, tell me what the general lighting load is. Now, if that's the question and it wants to know what the actual general lighting and receptacle load is, this is before any demand factors have been applied here. So be careful on how they ask you the question. So in this case, remember what we said for the general lighting? It was based on the square footage times 3 VA. That was 5,565. But you also add the small appliance, which in our case was 6,000. But remember, on the exam, it could be the minimum of 2. If you have 6, you got to count for, or you have 4, you got to count for 4. If you have 8, you got to count for 8. Okay? In our case, we had 4 small appliance branch circuits. So it's 6,000 VA, 1,500 apiece. And then your laundry circuits are 1,500 apiece, but we had 2 of them. So that is 3,000. All right? So if it asks you what the general lighting load is before you apply any demands or factors, then you simply add these 3 up. Okay? And that would be what you would be your general lighting receptacle loads. All right? Now, if they ask you what it is after the demand factors for the general lighting and receptacle loads, or the general lighting and small appliance and laundry loads, then you get to apply some demand factors in 220.42, right? So, and that's under the standard method, okay? So this is what you get right here. So if you see the example we just did right here, so it depends on what they ask you on the exam. If they just want to know what the general lighting receptacle load is, or here's another way they might ask it. Are you ready? They might say, what is the general lighting and receptacle calculated load? Or they might ask what the connected load is. So the connected load would be the full value of just adding these up. The calculated load is a fancy way of saying what is after the demand factors are applied, and that's where you would apply the demand factors in 220.42. So look for those things on an exam. If they just want to know what the connected load is, that's the load that's connected before they do any demand factors. Then answer the question that way. If they want to know what the calculated load is, then it means you had to do some type of calculation and apply some type of demand. And that is where you would use table 220.42. So the first 3,000, 100%. From 301 to 120,000, or we like to say the next 117,000, because that's from 3,000 up to 120 is going to be 117,000. But anyway, keep it simple. 100% for the first 3,000, 35% from 3,001 to 120,000, and 25% for the remainder over 120,000. They're very rarely ever going to have any general lighting in a dwelling that is going to be over 120,000. So, and you're not going to get that on an exam as well, okay? You don't do 125% for lighting because this is a dwelling, single family dwelling. There ain't no luminaire. The code doesn't account for you turning lights in a residence on and leaving them on. No, that's up to you, okay? There's enough fudge factor that's built in here. That's up to you. You only apply the continuous load for commercial applications, not for residential. Okay? So, in this case here, you would be the first, so let's add it up here. So it's 14,000. So we do 14,565. Take the 3,000 away, and you're going to use that full amount and set it to the side. Take whatever the remainder is, and that is 11,565. Do that by 35%, because obviously that's not going to exceed 120,000, so we're good. And so 11,565 times 35% is 4,047.75. You can check my math to make sure. And so there. And then what you do is now we're going to add the 3,000 back to it, because we had to take that at 100% anyway. So it's better to separate it out and then apply the 35% to the remainder, and then you can add your 3,000 back. So again, this was rounded, 4,047.75. The code says that anything 0.5 or greater, I can round up. So we rounded up to 4,048. Plus we add the 3,000 back. So that gives us 7,047.75. But remember, we rounded. So that's why we have 7,048. Now that is your general lighting and receptacle calculated load. Okay. And incidentally, in the Fast Tracks program, that would be the very first thing you do in your program when we're doing single families. That would be what you would work out. Okay. As the first 3 or 4 steps that you would do. Okay. So we've taken care of all this right here. Right? So, and the next thing we want to look at is the appliances that are in a dwelling. If we have 4 or more fastened in place appliances, then we get to take a demand factor of 75%. Now, how does this differ from the optional method? The optional method, we get such a big demand factor. Again, the first 10,000 at 100 and the remaining at 40%. But in the standard method, we're getting all these demand factors piecemeal, little pieces. So logically, the next step after we did the general lighting and small appliance and laundry and things like is to move on to appliances. If you have 4 or more fastened in place appliances, then I can apply a 75% demand onto that. And that's under 220.53. So in our equation we did a minute ago, these are all our appliances. Now notice in this house, we also have 3 attic fans, okay? Very much treated as appliances, okay? You buy them in standardization. They are appliances. Don't get your mindset thinking that appliances always have to be a dishwasher, okay? All right, so we took the water heater was 4.5 kW. Remember, we always want to convert that into VA, okay? So 4.5 times 1,000, that's what the K stands for, 1,000. So that's going to be 4,500 VA. We have a dishwasher. Again, it gives us this 10 amps. Well, one of the things that you're going to be used to doing on an exam is you're going to have to get used to converting to get VA. So if they give you an amps and they give you a voltage, okay, then all you got to do is multiply. And they should have, to be honest with you, they should have an ohms wheel. Okay? They should have an ohms wheel. They should give you an ohms wheel during your exam, okay? All right, so 10 amps times 120 volts is 1,200 VA. Write that down. In waste disposer, half horsepower. Also, tip, anytime on your exam, if they were to ask you anything about horsepower and it gives you the motor, you immediately should know that you're going to have to go over to the tables in 430 for motors. If it's single phase, it's 430.248. If it's 3-phase, it's 430.250. Then you need to find that motor. In this case, it's a 115 volt motor. It's a half horsepower. When you go look that up, you're going to see that it's 9.8 amps. And once you have the amps, then you can do just like what you did with the dishwasher. You can go amps times the volts, and that's going to give you the VA because you want the VA. So do that immediately on an exam. Anytime you have horsepowers in one of your examples, you got to remember, okay, I need to convert this into amps so that I can then do a simple math, and that is the amps times the volts equals the actual VA value, okay? All right, trash compactor, it tells us the amps, tells us this. Now, another tip, don't try to outthink the exam question. If it tells you to use 120, and it says it in there, use 120. I have a lot of people that will do in-sync waste disposal and see 115 and a half horsepower, and they think because the house is a 120/240 that they have to use 120 here. Don't. Use the 115. That is what's in the question. All right? You don't want to try to convert that and say, oh, I'm going to treat this as 120 because I know that a house is 120/240. Use what's in the equation. Use what they give you. The only reason the 115 was significant because when we go back to motors, everything's broken down into like 115, that type of thing. It's not going to be 120, 240s and things. It's all going to be broken down in what the motor rating is. Okay? So in this case, that's a 900 VA for that trash compactor. 7.5 amps times 120 volts. That's what's on the screen. And then the amps. Now, each one of these fans are 4.2 amps times 3 of them. And that's where you get the 12.6 amps. But see, we got the amps and we got the volts, so it's no big deal. 12.6 times 120, and that is 1,512 VA. Now, all of these fixed appliances added together, 4,500, 1,200, 1,127, 900, and 1,512 is 9,239, I guess, because I'm not checking my math, but that's what it is. Now, I have, how many fixed appliances do I have? I've got 5. So I'm allowed, at 4 or more, I can apply the 75%. You might get a question on an exam, and if you're in Texas, you very much will get probably an exam question like this. They're not going to ask you to calculate a whole dwelling. They're going to ask you to be able to do any separate component of the calculation. So if the question is asking about appliances, then you just need to remember that when you have, and it tells you that you use a standard method, then you know that if you got 4 or more, then I got a demand factor of 75%. Okay? And then so it's 9,239 times 75% is 6,929.25. I get to drop the 0.25 because of that rule that says 0.5 and greater, we round up. Less than that, you can drop off. So that means it's 6,929 VA. And if the question asks you, what is the calculated load for these 5 appliances, okay, then it would be 6,929. If it asked you what the connected load is, it's what? It's 9,239. So understanding the terminologies is going to help you out, okay? All right, so clothes dryers. Interesting thing about clothes dryers, guys, is clothes dryers are not a requirement of the code. But if there is a clothes dryer there, then I have to take this value and I have to utilize it for my calculation. Okay? So the clothes dryer must be at least 5,000 watts. Okay? But notice what the code says. So if one of the circuits for the feeder calculated dryer, and ours was 5,500 kW. Okay? So it's either 5,000 or the nameplate, whichever's larger. Okay? For the standard method, you're not just taking flat out nameplates, whether or not even it's less than 5,000, that's an optional method. Under the standard method, it's either 5,000 or the nameplate, whichever is larger. In this case, our nameplate's larger. It's 5.5 kW, which is 5,500 VA. So that's our dryer load. That's simple. Done. Now, when you're sizing the neutral, you can take 70% of this value, okay, for the neutral, okay, but not for the hot conductors, okay? When you're sizing the ungrounded conductors, it's 5,500 VA. If I'm sizing the neutral in my load calculation, as you do once you get all your values done, then it would be 5,500 times 70%. So then it'd be 3,850 VA for the neutral contribution, okay? But we'll look at that in a second. Cooking appliances. Pretty much, I encourage you to go watch my video on ranges because I go through all of the notes and everything when it comes to ranges. But let's look at this example here. I have a counter-mounted cooking unit, 7 kW, and I have a wall-mounted oven, 6 kW. Now, we're not sizing a branch circuit, okay? That would be note 4, okay? We're not sizing a branch circuit. We can put these together and treat it as one range. Okay, we're not doing branch circuits here. We're doing load calculation for a service and feeder, okay? So we would use note 1, note 2, and note 3 where applicable, depending on what we're dealing with. So in this case here, all right, we have 7 kW and 6 kW. All right, they're all more than 1.75 kW or 1,750, so we're good to go. We can apply some demand factors, and we get to use table 220.55. Again, neutral, 70% of the value that we calculate in a minute can also be applied for the neutral, but we're not sizing the neutral right now. Now, I have people that do this while they're studying. They will go on and size a neutral since they're already doing this anyway. They would take the appliance ultimate load that we calculate, and they would do that at 70%, and they would write that down in parentheses beside the load value, and they know that when they go back to do their neutral load calculation, they already have done the math, and they don't need to do it again. That's totally up to you. Now, the forms that we use in our program, you're just going to fill in the blanks. It'll work you through it. Okay, don't overthink that. All right, so we have a 7 kW. It's right here. We have a 6 kW right here, oven. Okay, bonus units fall within column B. Okay, they both are in column B. So I can always have to use column C unless we can utilize column B. Now, why do we get to utilize column B? Let's go to the code so you can see that. All right, so I'm in the code, and we'll just go real quick to 220. 50. Okay, so right here was all the stuff that gives me the permission to use the table. Okay, so this is the table we're talking about. Now, notice it says use C. Okay, this column will always be used right here, except otherwise permitted in note 3. Well, what does note 3 say? Well, note 3 says for over 1 3/4 through 8 3/4, which again, ours are 7 kW and 6 kW, right? I mean, that's what our values are. So we're good. We fall in this category. It says in lieu of the method provided in column C, which we could just go to column C, but that's not going to offer us the best choice. It shall be permissible to add the nameplate ratings of the household cooking appliances rated more than 1 3/4, but not more than 8 3/4, and multiply the sum of the demand factor specified in column A or column B given for the number of appliances. Okay, we have 2 appliances, by the way. All right. Now, where the appliances fall under both A and B, then you do one of the appliances under A and one of the appliances under B, and then you add them together. But both of ours fall under column B. Okay, so here we had 2 appliances, a wall-mounted oven and a cooktop, and we fall into B, so it's 65%. Now, don't forget, this is a percentage. This is actual kW. Okay, so we could choose either 11 kW, because that would be true column C, or we can do it at 65%, right? 65% of our nameplate values that get added together. Now, whichever one results in the smaller size or the lower value, we can use that value. Okay, so let's kind of go back to the PowerPoint. Now that we know it's 65% is what we're going to use in our value. All right, so as you can see here in the PowerPoint, we're going to take, there's 2 units. We're going to do column B because we knew what 11 was. It was 11 under column C, but we're going to compare it. So 2 units at 65%. So you take and add the 2 together, 7 and 6, it's 13. And you multiply it by 65% of the calculated load. So it's 8.45. Now let's not trust anybody. Let's do it ourselves. 13 times 65% is 8.45. Okay, I did it. So that's 8,450 VA. Okay, and then remember, watts or VA are synonymous in these calculations. Okay, so 8,450 VA, isn't that less than the 11,000 in column C? Absolutely. So I get to choose the 8,000. That's why you compare the 2. Okay, but only if the notes allow you to under note 3 to do so. And in our case, it does, right? Because these range and both of these fall under column B. Okay, and it all falls under the sizes allow me to be under what? Column B because of the sizes. See if I have any questions on that. I don't have any questions. And I don't see where I'm dropped any screens, so there might be a delay, but it looks like we're okay. If anybody has any questions so far? So that would be our cooking appliance application. So the next one for people and purely under the 2017 code, because that's what most people are testing on. This is the one where, based on what they give us, we have to compare the heat versus the AC. Okay? And in this case scenario right here, it looks like we have electric strip heats in there. We have 3 banks of them, and it's in the air handler. So the blower is going to not only blow, okay, so it's air conditioner with the supplemental heating package. That the blower is going to be blowing the heat. Okay, so, but it's also going to be blowing what? The air conditioning. So when we're comparing the heat versus AC, and this is a very common exam question, where it's going to ask you is about comparing heat versus AC. Okay, we want to take whichever one results in the larger value. So it's a little different than what we did for ranges. There we want to take the larger value. So we're going to compare the heat versus the actual AC. Now the good news about this one is that none of these motors are given to us in horsepower. So we don't have to go venturing back into 430.248 or 250. We don't have to deal with that. We could just use simple multiplication and come up with our values. All right. But remember, use the values that are given to you in the question. All right. So the heat is going to be, we're going to compare the two. So the heat's going to be 15 kW, and we're going to convert this to VA, so that's 15,000 VA. And the air handler, which is 3.2 amps at 115 volts. So we have to do the math. Okay, so I'm going to do 3.2 times 115, and that is 368. So you're going to write that down, 368. That gets added to the heating load. Why? Because that blower for that fan in the air handler is still blowing the heat. So it's going to be on when the heat is running. Okay? Otherwise, how are you going to push this heat around anywhere? Okay? All right, so in this case here, all right, now, important question. If the heat was something different and it wasn't part of the air handler where the blower wasn't being utilized with it, then I wouldn't add the blower. Okay? Some other type of baseboard heat or something like that, okay? Gets treated totally different when you get to optional method. But I treat those loads as those loads, and those are still heat, so I'm going to compare them. But in this case, it's one complete unit, okay? And so just look at how your question gets asked, all right? So in this case here, it's 15,000 VA, plus we're going to add this 368 to it. So that'd be 15,368. Now, compare that to the AC. Now, what's the AC going to have? It's going to have the blower. It's going to have the air compressor or compressor motor outside. And it's going to have the condenser fan motor. All 3 of those things will be running at the same time for the AC. So I got the 368 already for the air handler blower. Next, I do 16.6 times 230 is 3,818. And then the next one was 2 amperes times 115. So it's 2 times 115. And that is 230. Again, on an exam, don't try to let your brain overthink this and say, but wait a minute. I know that the circuit in the house is 120, 240. Use what they give you in the question. Okay? This is exam world. This is not real world. Okay? Examo world. All right? So, next, I'm going to take and add those up. 3,818 plus 368 plus 230. And that is 4,416. That is my AC. Which is larger? The heat. Which do I get to discount and get rid of? The AC. The AC is gone. It's out of here. And all I have to do is account for the heat in my load. Now, alert for those that are on the 2020 exam. If the same question was asked of you on the 2020 exam, it's a little different. I'd have to take the heat and compare it to the AC, okay? But if the heat's larger and the AC is omitted, I still have to take the largest motor in the building, okay? And in this case, if the AC motor was the largest motor, which in this case it would be, the compressor is 3,818, I have to take that value at 125%. Okay. So again, that's a little bit of a change for the 2020 code. And even if I add that, and I have to add that value to my heat load. Okay. I'd have to take that value and add it to the heat load. So it wouldn't be 15,368. It would be in addition to the 3,818 VA plus the additional 25%, right? And because that would be the largest motor. So boom, that's how it would apply. And so it would just make my value get up higher, okay? 2017 code, you don't do that. You don't do that at all. And in the 2023, we're going to probably change that because it's not really shouldn't be done the way I just told you in the 2020. It's a problem. You don't need to do that. The 2017 code is the right way. Take the heat or the AC, omit the one that's the lower one, and take the one that's the largest one, and you're good to go. Okay? So anyway, the heat wins here. Okay? All right, after this is all done, one of the things that you have to look at is if I took the heat, I didn't take the AC. So next one I have to look at is what is the largest motor in this building, in this house? And I look at all the motors, okay? I don't look at a dishwasher because the motor is part of the appliance and it has heating and it's all a package deal. I look for any motor that's has a motor involved in it. Like the in-sink disposal is nothing but purely a motor. The trash compactor is a motor. Okay, the fans, motors. And I have to find whatever the largest one is, and I have to add an additional 25% to it. Okay? And this is all covered in 220.50, but it says you take motors at 125%. Why are we only taking 25%? Because we've already taken the motor. Remember when we did the appliances? We already took the motors at their rating, 100% of their rating. We already did that. So this is saying, I just need you to tell me which is the largest motor, and I need to take it at additional 25%. So how do we do it? Find the largest motor in VA. In this case, it was the disposal, which was 1,127 VA, because remember, the AC was omitted. So once it's omitted, it's gone. Okay? So in this case, I'm taking the motor under the 2017 code, and that would be the waste disposal. And I'm going to take its value and do it times 25% because I've already captured the waste disposal one time. I've already done that math. All I need to do is get that additional 25%. And that's what we take the 1,127 VA times 25% or 0.25. That's 281.75. We rounded to 282. Okay. And that's what get put into the largest motor equation. And we just simply add it up. And again, the dishwasher is a combination appliance. It doesn't qualify under the motor rule. All right. So we did it all. We added our general lighting. We did our fixed appliances. We did our clothes dryer. We did our cooking appliances. If you remember, the heat is what won. We took the largest motor at 282. We add all them up, and we get 43,577. We divide that by 240 volts. That is our 122 40-volt system. We do it by 240 volts, and it's 181.57 amps or 182. Because of the 0.5, we round it up, and there you go. And then we go select the conductor accordingly. All right. And so this is what we did. So we had 182. We went to 240.6A, and there isn't one for 182. So we ended up at a 200 amp device, and that is perfectly fine. Not a problem. Okay. Let's see. Before I go into this one, which could be using 31015B7, do we have any questions? Anybody got any questions so far that I can go back and rehash it? Because I'm talking quick and there's a lot of info. And I don't see any questions. And again, of course, I don't know that you're all still with me. But I said I was going to cover an awful lot of stuff and an awful lot of topics tonight. So if you do have questions, please feel free to post them. And there's going to be a certain number of people out there where they're going to say, Paul, you just went too quick, too fast. I get it. That's why you need a program like our Fast Tracks program, which will go over each one of these pieces, piece by piece by piece by piece. Chris, if you're still in it, you're starting in the Fast Tracks program. It is going to walk you through each piece. Okay? So everybody, somebody let me know you still can see me, you still can hear me, so that I can continue on. Hopefully you can see me or hear me. I'll wait for that confirmation. I should probably log on to see if there's a delay because nobody's saying anything. So I will go and see, because again, I'm not getting any responses. So I want to. And I'm looking down and mine. And I'm looking down and mine. Oh, see, there's that little delay there. But I see. Let me see, because maybe my chart, maybe this is probably what needs to be. This probably just needs to be refreshed. Let me refresh this, because for some reason I'm not seeing you guys. Okay, now it came back. Okay, so does anybody have any questions on anything? Again, I went really quickly. And I apologize because my wife came in and I remember I thought I was going to have to rush, and she's telling me I've got a little more time before I have to go. She's on the other line. Most of y'all have never met Darlene, but she also works here with me. So, we're working late tonight, and we're working with an editor for a project that we're doing, and I've just got to talk to them, and she's letting me know. What did I go over? Is anything that I went over before I get into this? Let me see if I can follow some questions, because it looks like I had some and then I didn't see the screen. So let me see. Chris. So it says you will need to add the condenser fan motor, AC compressor, and the air handler blower to calculate the AC. Yes, Chris, because you have a blower that blows the air, that's in the air handler, and then you have the outdoor unit, which has the actual condenser, and then there's that fan that runs the fan motor that keeps it cool. So you've got the compressing condenser, you've got the fan, and then you got the air handler inside that blows the air over the coils that are inside in order to blow it through the building. So you have all three of those things have to be added together. Now, the reason that we added the fan for the heat is because it has 3 strips in there for electric heat. And that electric heat, in order to get it out through the building, in my example, has to have that fan blowing to move it into the duct system. So obviously, if the heat's going, the fans are going. So that's why I have to add that load to the heating load, because again, it's part of the heating load. Okay? So that's why we added that. Hopefully, let me know if that answers your question. It says on the range, was it 13? Don't you have to want it? No. So Larry, the reason we don't is because, remember, we use column B, 2 separate ones. And under column B, it says that you could treat the 2 appliances, you just add the nameplates together, right? You add the nameplates together, and at that point, you compare it to column C. And it came out less. So I didn't have to do the 13 because I'm not treating them as one. I'm using note 3 to add them together. And if you read note 3 in 220.55, it tells you just to add the sums together, okay? And once you apply the percentages. So I added the sums together and applied 65%, and that's my value. So I was allowed to use that. Now, that's the difference, okay? Now, if I had one range in your calculation, if I get one range, for example, and it is a 13 kW range, then you're absolutely right. Then I would have to apply that rule. I encourage you, Larry, to go watch my range video. And I need to do this to make sure that it's still going, so that it's not stalled. And it looks like shadow roof was the last one. So still going good. Okay. All right. So now, any clear on that? So just remember that you have the steps you got to remember for an exam. If you're going to do a load calculation for a single family dwelling and it's a standard, that's typically low-hanging fruit on an exam. They might ask you the general lighting and general receptacle loads. It's just the dimensions of the building, outside dimensions, times 3 VA per square foot. Okay. Minimum of 2 small appliance branch circuits at 1,500 VA each. 1 laundry circuit at 1,500 VA. If they ask you what the connected general lighting and receptacle loads are, then it's just the full value, the VA before you apply any demand factors, right? If they say what is the actual calculated load of the general lighting and general receptacle, or they say what's the general lighting or general receptacle demand value, then you have to use table 220.42 to apply some demands. That's the first 3,000 at 100%, and the next 301 to 120 at 35%. Okay? And that would be the answer for your what is the calculated load for the general lighting and receptacle appliance and small appliances and laundry loads. Okay? So again, just work on those. Now, remember, appliances fixed in place, 4 or more, you get the demand factors of 75 applied to the value. Okay? You get a benefit. You get a break. If it's the dryer in that stage, in 220.54, in the standard method, it's 5,000 VA or 5,000 watts, which is synonymous with VA, but you want to convert everything to VA. If you do that, then you're going to take, if it's 5,000 or the nameplate, whichever is larger. So you just take the 5,000. Okay? Another question, if you get an exam, and they don't say nothing about a dryer, don't think you got to add a dryer, because you don't. You don't have to add a dryer. Dryers are not required. Okay? So, just remember that. But if they put a dryer in there, then you have to add it into your calculation. For ranges, again, in our case, it was 2 ranges. They both fell under column B. So I had the ability to use note 3 and compare it to column C. And I did so. And it was actually a better value under what? It was a better value under B. And so that's the value that I took. Okay. AC versus heat. Remember, if you get a question on the exam, it's whichever is larger, AC versus heat. Okay. The laundry room was 1,500 VA. So you should, if you're doing the requirements of branch circuits that are required are the general lighting and general use receptacle applications. That is 3 VA per square foot. Minimum of 2 small appliance branch circuits at 1,500. A minimum of 1 laundry circuit at 1,500. Okay. And those are the only VAs that are required. Now, if you have other applications to be aware of, then if you've got if the exam question tells you got 5, okay, laundry circuits, then you know that it's 1,500 times 5, right? That type of scenario. If they say in the exam that it's 6 small appliances, then it's 1,500 amps, 1,500 VA times 6. Just think about your calculation. If they don't tell you, but they ask you to do what is the general lighting and receptacle demand load for and they tell you the square footage of a building or whatnot, then you got to have at least 2 small appliances. You got to have at least 1 laundry if they don't say otherwise, and you've got the 3 VA per square foot. Okay, and then you can apply the demand factors in 220.42. So just remember those little things that you run into. If you're in the Fast Tracks program, it will literally walk you through each one. Now, one important thing I want to tell you before you go away from this concept is anytime you get an exam question, this is important. Anytime you get an exam question where they tell you it's a dwelling unit and the service is between 100 and 400 amps. Okay, and 100 and 400 amps. And they tell you that the panel handles 100% of the load, then you get to use the benefits for sizing the conductors based on 31015B7. Okay? Remember that. And this is what we're doing up here. So let's say I have a service coming down through the meter, and like you see on the screen, and it's going to a 200 amp overcurrent device. Okay? This is the rating under the allowance in 31015B71 for the service. This is 200 amps. So this conductor right here cannot be less than 83% of this service rating. And that little table that's in the code that was in 31015B17 that disappeared and went back to the went back to the calculations in the Annex D, that comes back in the 2020 code. But who needs it? You really don't need it, because all you got to remember is the 0.83 or 83%. That's what that table was based on. And that means that there's no other adjustment or corrections taking place. It's just a pure question. They're asking you, what is the minimum size of these conductors? Now, could I size it based on the 200 amp breaker under 31015B16 and be 3/0 copper? Yeah. But you always want to answer to the best possible answer in the code. So even in our Fast Tracks program, always solve it for the best possible answer. And as me as an electrician, the best possible answer is always going to be the smallest conductors possible, because that's going to save me, money, and it's not oversizing it. Okay, so in this case, it would be 200 amps times 0.83 or 83%, and that would be 166 amperes. Okay, now, what am I going to do for 166 amperes? Conductor sizes? Okay, well, we'll go to the code, because once I know that, depending on the terminals that are rated, in the case, let's say these terminals, since this is over 100 amps, then it's going to default at 75. Okay, so we're going to go to the code, and we need it good for 166 amps. So in the code, we're going to go to 31015B16. And it looks like we would be a 2/0 copper, or we would be a 4/0 aluminum. So now you know that's actually where they get the values that are in that table. It's based on 83%. Okay? Now, that is probably one of the questions that gets seen on an exam, is they want to make sure that you know how to use the bare, 31015B7 application. They want to make sure that you know how to do it. And so that's one of the examples for that. Now let's go back to the PowerPoint so I can kind of show you some applications here. All right, now that would be resulting in, obviously, a 2/0 copper or 4/0 aluminum is what this could be. And that's why you see people do a 4/0 aluminum. And that's why it's traditionally been okay. Why? Because the 4/0 aluminum is good for 180 amps. Now, even if you didn't use this rule, I'd still be okay to put that on a 200 amp breaker, because I could do the 180 amps, and since a breaker doesn't correspond, I can go to the next size, which would be a 200. But the load can't exceed 180 amps. But it would allow me to put a 4/0 on a 200 amp breaker, even if I wasn't using this rule. Okay? Now, what about when you're dealing with feeders circuit? Okay, so here's meter coming. This is the service. And now we've got a feeder downstream. Same rules apply. Okay? Can't be less than 83%. Same rule. So this is a 200 amp breaker, but now this is protecting the feeder. Okay? So if the feeder is rated 175 amps and no adjustment or corrections apply, then the math is simple. Okay? But in this case, let's say it was a 200 amp rated device. Be 200 times 0.83 equals 166 amps. The same rules apply, but it has to supply 100% of the load. Okay? I can't have a panel here and then feed an air conditioning unit right here and then feed this panel. Then I could not use this rule. I could not use the 310-15B7 rule. Okay? All right. Now, another thing I'll tell you, this only applies, okay? This only applies if it handles 100% of the load. Okay? If these feeders are seeing 100% of the load on the load end of those feeders, it's only time that it applies. Okay? Now, when doing the neutrals, only thing I'll tell you here in the neutral is that everything that's not 240 volts or 230 volts has to be added into the calculation for the neutral. So all of the small appliances use a neutral. All of the laundries use a neutral. All of the 3 VA per square foot, all of those general use circuits are going to use a neutral. So they all count. The dishwasher uses a neutral. Disposal uses a neutral. Trash compactor uses a neutral. The attic fans use a neutral. Okay? Now, you notice the dryer and the cooking units are not highlighted here because remember, they get that 70%. Right now, we're just looking at the ones that only are going to be the 120 volt applications or 115 volt applications. And we've already done the math for all of these. So all you have to do is regurgitate those numbers because we've already calculated those when we did the standard method. Okay, so here's what we did. We took all those values. That didn't change. Now, remember, we took the appliance values. The only one that we leave off is the water heater. Okay? Now, remember, if I have 4 or more, I still get to apply that demand factor. Just because we're doing neutrals, I got to apply it where? At the ungrounded conductors, I ought to be able to apply it to the neutral as well, right? Makes sense? So I take all of those again, just leave off any of them that are 240 volt or 230 volt, and I do the same thing I did before, add them up and apply 75%, and my neutral load is 3,554. Clothes dryer, remember it was 5.5, and the cooking was 7 and 6. We already did the math for those. Remember, it was 8,450. And remember, the dryer was 5,500. Do it times 70%, and that's the 3,850. We already did that. And then take your actual range value that we calculated earlier and do that at 70%, and that is 5,915. Okay? Now, move on to the air conditionings. Okay? We don't account for this place here, we don't account for the 230 volts, okay? But we do account for any of the loads that we were dealing with that actually had what? Okay? Any of the things that we actually had that were dealing with 120 volt loads that we're going to calculate in, okay? And of course, we had to get the largest motor. So we added it all up, and this is what we got. And here's your neutral. There's your general lighting. There's your fixed appliances. There's the dryer. There's the range. There's the air handler motor, condenser fan motor. Okay. And here is the largest motor, which took the largest motor at 282. I believe that was the in-way sink disposal. And you just add them up the same way, and you come up with the VA value and divide that by 240. And in our case here is 21,240 divided by 240, 88.59 or 89 due to the 0.5, rounding. Then it would be a 3 gauge for 89 amperes per 310-15B16 or 2 gauge copper for 89 amps, 310-15B16. Okay? Went over that really quickly. Anybody have any questions on that? Please feel free to them. Now, easiest thing I'm going to tell you to do is make sure you go watch the video because we have the videos on this where I work through each piece and I explain each piece. Okay? So, want to make sure that we work through it. Just remember, when we go back into the neutral loads, we don't care when it does heat versus AC. We want to take all the neutral loads. Why? Because those neutral loads will be going when it's running, whether it's heat or AC, and the heat didn't have any anyway. So in neutral, you take all the 120 volt loads and 70% of the range and a range application and 70% of the dryer, and you add them all up. Okay? That's what you do for neutrals. So when you're doing an optional method, for example, it's very similar. We're not going to do voltage drop tonight. Let's see here. Hold on, let me make sure which one I'm going to here, guys. I told you I'm winging this thing. Let me get rid of that standard one. And let's go to the optional. Okay, let me... Bear with me. I don't even know which one it is here. There it is. Okay, so the optional method using the same values, I'll go through this one pretty quick because it's pretty simple. Same values, nothing changes. The optional, same values, the outer dimensions, nothing. Here's the thing. People freak out when they see optional versus standard. The standard's much harder. Once you get to the optional, as long as you know how to do the standard, the very first part of it, the dimensions and the small appliances and the laundries and everything like that, then everything else is pretty simple. So, same dimensions, remember, 35 by 55, and you got to take away the porch because, again, that was an open porch. So, in that case, it's just 1,855 VA square foot times 3 VA, 5,565. And that's where you get it right here. You still got your small appliance brand circuits. That doesn't change. There's 4 of them in our calculation, so it's 1,500 VA each. Remember that on an exam, minimum of 2, but if they show 4, you got to add all 4. And we added 2 laundry. Remember, the code says it only requires 1, but if you have 2, you have to count for 2. So in this case, it's 2 of them, so it's 1,500 VA each, so it's 3,000. Notice nothing changed so far. Nothing has been dramatic yet, okay? Now, same question is all of these together. You didn't do anything differently, right, than you did with the standard method so far, okay? What you're doing is you're going to add them all up, and that is 14,565. Now, unlike the standard method, okay, where we applied this 220.42 table, okay, we're not going to do that here. You're just going to take those numbers and set them aside for a second. That's why it's different, okay? It's different than the standard method. Now, let's talk about these appliances. Now what's different than the standard method? Whereas the standard method, you got to apply 75%. Here, no. Just take the values, okay? So in this case, the water heater was 4,500. The dishwasher, remember these values, 1,200. In-sink waste disposal didn't change, 1,127. Trash compactor is 900 VA, and all 3 of the fans together was 1,512 VA. Add them all up, 9,239. Okay? That's your total fixed appliances. So the fasten in place appliances is 9,239. But wait, if we look at 220.82b, we also include ranges, wall-mounted ovens, counter-mounted cooking, clothes dryers, and water heaters as well at their nameplates. So what do? 5,500 VA or 5.5 kW, which is a synonymous with 5,500 VA or 5,500 watts. We want to convert to VA, which makes it easier. We're taking it at the nameplate. So it's 5,500, boom, okay? Now, remember what we did before? Remember that all the values that we had and everything we're adding up, all these appliances, adding everything up. We took that 9,000 and we're adding now this 5,500. So that gives us 14,739. But wait, we're not done. Then we get to the cooking. So we carried over that value. Now the cooking is 7,000 and 6,000. What do? You take them at the nameplate. Boom. Not complicated. You just take it. So that was 14,739. You add the 7, you add the 6, that's 27,739. But we're still not done. Okay? Now, we take and add all of our math values together. Okay? We had the general lighting. And if you kind of go back and you'll see that we took the 14, the 7, and the 6. And let's double check our math. Okay? Because again, this one is an old one, so I want to make sure that I've got all the values together. I've got the 9,000. Let's see here. Do the math with me. So it's 14. Let's do this because I don't trust this is an old template because I told y'all I grabbed the closest one tonight. I was not prepared tonight. Sorry. That's what you get when you get free training. All right. So I added that. And then I had my appliances. So I had 9,239. Got it. And I had my dryer, which is 5,500. Got it. And I have my 2 of these, which is 7, 8, 9, 10, 11, 12, 13. So I've got 13, so I add 13 to it. Okay. All right, so what I should have is 14,565 plus 9,239 plus 5,550 plus 13,000. Now I think what I did was I just shortcutted this up here. So let me double check this math. 9,239, you should be doing it with me, plus 5,500, plus 13,000. Yes, I already had added all those together to make it easy. So this 27 value here was all of the value. I added the the appliances, I added the dryer, and I added the 13,000 for the cooking. I added it all together already. So this was the general lighting, and this is all of the cooking and dryer and everything already added up. So it's 42,304. We want to check that math. Somebody check that for me. 14,565 plus 27,739. 42,304. That's right. So now the first part here, demand factor, and remember, we still haven't done heat, right? We're just doing the first part. The first 10,000 at 100% and the remaining at 40%. So we take the 42,304, take the 10 away, so we got something to work with. So that's 32,304. We times 40%. That is, and let's just do the math to make sure. So it's 32,304 times 40% is 12,921.6. So 0.5 rounding, it's 12,922. Now we add that 10 back because remember it said the first 10,000 at 100%. All we did was take it away, so it made it easier to apply that 40%, the multiplication. So then we put it back. So that is 22,922. Okay? So that was the B part. That's dealing with the receptacles. That's dealing with the appliances. That's dealing with the dryers, cooking. Now we go to part C. Okay? So you take this value, you sit it to the side. Now under part C, you've got a couple different options here. Now, it was pretty easy under the standard method. You compare heat versus AC. Under the optional method, you take it and compare whatever's the larger of all the options you have. And we'll look at each one of the options. Okay? Now, the first thing we do is we want to make sure we convert all these into VA. Again, just like we did before, just going to make it easier to do all that. And we've all done it. So we've converted everything. Okay? Because nothing really changed here from our original equation. Now, 282C1 says, number one, it says the NEC says 100% of the nameplate rating of the air conditioning and cooling. So what is 100% of that first? So this is the first option, okay? This is 220.82C1, and we'll look at that in a second so you can see all the options. But we already know we have an AC, so we got to do this anyway. So we've already kind of done this already, didn't we? Even under the optional method, we've already really done this. We took the the air conditioning at the total was 16.6 amperes times 230 was 3,818. That condensing fan was 2 times 115, which is 230. And of course, that air handler is going to be at 3.2 amperes times 115 volts. That's 368. So that's 4,416 VA. That is 100% of the AC. Okay? So write that down, because you just need to write that down. That is C1's value. Now, C2 says, and I'm just going over this in case this is in your exam question. C2 says the AC says take 100% of the nameplate rating of a heat pump where the heat pump is used without any supplemental electric heat. Okay? Now, well, since we just did 220.82C1, so nothing additional is needed here, plus it says do this without any supplemental heat. Okay? And so we do have heat. So what we're dealing with is not a heat pump. But if it was a heat pump in your question, okay, then they're going to give you the nameplate value, and you take it at 100%, and you compare it to the other ones, the AC, compare the heat pump, and you would take whatever one's the largest. All right, the next one says, well, what if I had, and again, it doesn't apply here, but it says, what if I have 100% of the nameplate rating of a heat pump compressor? So you have a heat pump, and let's say it's got supplemental heat built into it. So it would be 100% of the heat pump compressor, okay, and that's whatever's on the nameplate. You take that ampacity, 100%, whatever that value is, you take it, and then you look at the supplemental heat, and you take that value at 65%, okay, and then you compare, and if that ends up being the larger, then that's what you would go with, okay. Now, here's something interesting. If you have a heat pump, and a heat pump compressor prevents the operation at the same time as a supplemental heat, which means that would be in your exam question. Now, hold on, make sure I didn't lose anything here from you guys. Hold on here, because I just got an error screen. It looks like I'm still going. Okay.